Good afternoon, everyone. Good morning. So today we'll be looking at the topic which is capturing uncertainty in neural nets. So previously we were dealing with things like sampling, rejection sampling, inverse CDF sampling. I purposefully took this topic because I thought one, it would give you a welcome break from just looking at some elementary methods, some basic methods which have been used in the literature. Second, I thought that this would make the course immediately practically useful because you will be looking at neural networks a lot in the kind of modeling that you're doing. So we could get some uncertainty of it and we can solve some practical problems out of it. So if you remember the first lecture that we had, in which we saw whether the person is a dog or a human, we said that the person was being we were very wrongly predicting the person to be a dog, right? If you remember that example. Instead, if we had used uncertainty via also modeling the epistemic uncertainty, we would have been able to say that we don't know much about this person, about this object. Right? So we'll be looking at two variants of uncertainties. The first one being aleatoric. Can someone quickly tell me what you understand by aleatoric uncertainty? So it's the noise in the, it's just trying to capture the uncertainty which is due to the inherent noise. But that also we have two different types. Thus far, the only kind of aleatoric uncertainty we've been considering is homoscedastic, right? Homoscedastic, homos meaning same, and skedasticity meaning dispersion. So it means that we have the same dispersion across all the inputs. So that is what we've been assuming. Can someone remind us how we've been incorporating homoscedastic likelihood into our models till now? With the Gaussian distribution, we've been saying that epsilon I is normally distributed with mean 0 and certain variance sigma square, right? So let me repeat that epsilon I is normally distributed with mean 0 and variance sigma square. That sigma square is fixed irrespective of the input. So that becomes your homoscedastic noise. I am going to be considering three variants of aleatoric uncertainty: homoscedastic with a fixed noise, right? The second one where we can learn the noise, so the first one we just say that this is the value of sigma square. Second variant, we say that let's try and learn the value of sigma square from the data. And the third one is heteroscedastic. So what do you think would be the kind of noise that we'll add in heteroscedastic models? Okay, so the noise which varies with respect to x, can you make it more specific? Epsilon I is, for example, epsilon I is a function of x, or the sigma is a function of x, right? And then the second kind of uncertainty is the epistemic uncertainty. This arises due to uncertainty in our model parameters. And the typical way to get this uncertainty is you put a prior on the model weights, you obtain the likelihood, you obtain the posterior of the weights. Once you have the posterior, you can then predict the posterior predictive distribution, which will give you the uncertainty over the predictions, right? But we've been saying that obtaining the posterior is hard. Why is it hard? On that side? Why is it hard to get the posterior? Sorry? It is trying to solve the intractable integration of likelihood times the prior, which is not solvable for many likelihood and prior pairs or pairs, right? So if in the case of conjugate distributions, conjugate likelihoods we're able to solve, but not for all distributions. So therefore we have to resolve to something like the Laplace approximation. The Laplace approximation does what? Can anyone quickly tell us? Right. So the Laplace approximation says that let us take the posterior as a normal distribution. The posterior can be any kind of a distribution. It takes it as a normal distribution with the mode being the map and the covariance matrix given by the inverse of the Hessian computed at the map, right? Where the Hessian is computed over the function which is negative log giant. So all of these things we have discussed till now. Now let's go back to the very basics. we will now be looking at how to specify all of these different kinds of uncertainties in our model. I have just imported Torch, NumPy, Matplotlib, Pandas. I'm interestingly importing a JAX library. So do you expect me to write a code which is working for both Torch and JAX? No, I will be looking at a very specific library, a very specific function from jax.treutil, which is going to be used for finding out the leaves of a nested dictionary. So for that purpose, I'm going to be using it, and then some functions to make the plots better. So we'll be looking at the different kinds of graphical models, for which I'll be using the following notation: the dark blue representing input node, filled out white circles specifying something which is trainable, and the dashed line circle has the non-trainable parameters. So without looking into the code further, can you just look at input, trainable, non-trainable parameters? Let's go back to the three cases that I've mentioned. First case is aleatoric uncertainty with homoscedastic noise, but the noise is assumed to be fixed beforehand. What is that you're going to be learning in this model, and what do you consider to be non-learnable? The sigma is assumed to be fixed, and what is not fixed? What is learnable? Neural network model parameters. Right. Second case, homoscedastic noise, but learnable sigma. So what is non-trainable in this model? Okay, so we're talking about parameters only. Everything is assumed to be learnable. We'll have to learn sigma, and we'll have to learn the model parameters. So let's go back and first create a very simple data set. I will be saying that the data set contains homoscedastic noise. So don't confuse with the model now. This is just a data set which I've specifically created, which contains noise which is independent of x. Right? So we create a function f, which is 0.5 x square plus 0.25 x cube. I have my epsilon I, which is coming as a normal distribution with mean 0, variance. What is the variance? Variance 1. And I multiply that with 0.2. I create y equal to fx plus epsilon. So y is the noisy observations, fx is the true observations we might have obtained if we didn't have any noise, and epsilon is the noise. And because I'm running this on the GPU, so therefore I'm moving things to device here. So then when we plot the data and the true function, you'd see that the dispersion across the line against the line seems to be constant. Irrespective of the input, we seem to have roughly the same distribution, right? Same dispersion across that. Therefore, homoscedastic, same dispersion. The first model is to create, so we want to create a neural network which can incorporate homoscedastic noise. So this is nothing that you have not seen earlier. We can first just verify that this is the graphical model that we'll have. We'll have certain inputs, x's. We'll have the model parameters theta. We want to learn a mu and a sigma. But sigma, I've said, is a non-learnable parameter for this case. So I'm only learning mu, right? So this is the same as the same simple MLPs that you've been learning till now. There we called this term as y hat, but I'm not calling it y hat, I'm calling it mu hat, right? And I'm calling this that there is some sigma which is now non-learnable. I'm keeping it like this. So the way we create such a model is just define a class which is a simple MLP now. I am creating 3 layers with 1 cross number of hidden cross number of hidden, and number of hidden cross 1. So it starts with 1 input, gives you 1 output. The forward is just running it through the layers and applying ReLU activation. But importantly, as I mentioned, my output is mu hat. It's not y hat. I'm calling it mu hat for now. Okay. So what do you expect this function to be? Loss, homoscedastic noise. I am giving it model comma x comma y comma params. What do you expect this function to do? What is the likelihood that we have assumed? It's a homoscedastic normal likelihood, right? So if you instantiate a model and you do a forward pass, what do you get? Mu hat, and sigma has to be fixed and has to be somehow given to the model, right? So the sigma I will be passing in the params for now. There are additional reasons why I am creating a params as a separate argument to this and not giving it a hard-coded value. So params has been passed, which means sigma has been passed. Model, if we do model of x, we can obtain mu hat. What after that? How do we get the loss? And we know the y also. Y minus model of x square, do you do that? But where does the sigma go there in that term? How do we compute the loss? Yeah, just, I think all of you knew the answer, but you were expecting a more difficult question. That's why you didn't answer. So firstly, I extract the log of the noise standard deviation from the params. So I'm going to be passing params as a dictionary in which one of the argument would be log noise standard deviation. Why am I using log of noise standard deviation and not just standard deviation? Here it's a fixed parameter. So because I wanted to make the code very generic, which will work across different things, and the point is correct that noise, so we can end up learning a parameter which goes negative, which does not make sense for our problem. So therefore, instead of learning noise standard deviation, we typically learn the logarithmic of it. But here it's going to be just passed as a fixed tensor. I can do model of x to get mu hat. I am just verifying certain shapes. Given the log noise standard deviation, I can apply the exponentiation on it to get the noise standard deviation. I'm doing some tricks to ensure that the shapes are all correct. Now the same thing which we've been doing throughout the course, I create a distribution object, normal distribution with the mean mu hat and the standard deviation noise SCD, and my noise and my loss is just negative log likelihood. So negative log prob, and that is the negative log likelihood. Right. So if I just look at this function, it goes from 1, 4, 4, 4, 4 to 1. Is the question you can ask? You can do mean, you can do sum, like they're equivalent, they're proportional. So I will create a fixed log noise standard deviation, which is just a fixed value. So I just take a logarithmic of 0.5. So what I'm assuming is that the sigma was 0.5. So I'm passing the logarithmic of that to this function. I end up creating this params dictionary, which contains the neural network parameters. Interestingly, I'm calling this homoscedastic model fixed noise dot state dict. Do we know what state dict returns? Let's just run it through this. Homoscedastic model fixed noise dot state dict. It gives you a dictionary containing the keys and the values. So just look at the state dict carefully, and then let's look at the something which is fairly similar to this. Homoscedastic fixed noise dot parameters. Okay, it's a generator, so if we put a list around this, okay. So the first one is 0.1564 minus 0.87, minus 43, minus 0.59. Do you see that they're the same thing with one difference? What is that difference? No, the bias is also there. So the bias was 0.028. The bias is also present here. What is the difference between these two? So it's a dictionary versus a list. That is one small thing, but I'm looking at something major. Requires grad, right? One of them specifically mentions requires grad equal to true, the other one doesn't. So that's something to look into. We will not immediately use this thing. I just leave it here in the notebook. Importantly, I call this, if I look at this function, loss homoscedastic noise, all it wanted was the model x, y, and params. And in the params, we were extracting out the log noise standard deviation. While I'm creating the params here, I am also creating some NN params, which actually don't use, right? It's just for keeping the code more generic. I'll show in a few minutes from now that why we could have used a more functional approach as opposed to an object-oriented approach of obtaining the same thing. So let's look at, we are passing in the x, y, and the params. And I just look at it from the current set of model parameters. What is the loss? It turns out to be 0.6247. I have a plotting function where I'll be plotting the x versus y, and I'll be also plotting x versus f of x, and I'll be then plotting x versus y hat. So one thing which I always recommend in such code is that you plot the predictions from the untrained model to get a sense of how it looks like. I will first show the output of the untrained model with the uncertainty importantly here. So the yellow line, dark yellow line, is the mean prediction. The black line is the true function f, and the red dots are the data points. And I see a lot of this variance. What kind of variance is this? This is capturing the aleatoric uncertainty, which I'd fixed to a certain value. So if I change that value, so this was set to 0.5. Let's say if I change to 0.1, you see that the noise variance has changed, but the mean remains the same, right? No? So let's see this at 0.1, and let's see this at 0.5 again, which was the value I'd set earlier. Right? I think there's also a visual artifact which makes it look slightly different, but the mean remains the same. The standard deviation is now just increased. Nothing else has changed. Importantly, the noise per input, the variance per input is the same. Right? So that is why it's a homoscedastic, and it's a fixed noise that we're giving at this point. Right? So nothing particularly useful for the dataset, which has been learned from the dataset. I'll have a simple train function. I am calling something known as parameter leaves equal to JTU, which was the JAX tree utils.tree leaves of params. And then I'm calling in an optimizer. So if you remember, the optimizer typically expects the list of parameters. That is what an optimizer expects in PyTorch. So if we look at the code also, class Adam, it is expecting params. Right? It expects a list of the parameters you want to optimize over. So we'll come back to this code in a bit when we understand the specific usage of tree leaves. For now, just assume that I am getting all the parameters in a list form. And then it's the standard for epoch and range epochs, loss.backward, loss function model xy params. And I am just again instantiating the model. I'm creating the params again. I'm passing in the fixed log noise standard deviation, which is log of 0.5. If I train this model, fortunately the loss goes down, and after 1000 iterations it is 0.311. So what do you expect to happen when I train the model? What will change? The mean estimate will change. Mu hat as a function of the input will have become better, but the standard deviation would have remained same because I've not done anything with that. So can you now see that the mean has become much better? It's much closer to the yellow line is much closer to the black line now, which means our mean has been better trained, but the aleatoric uncertainty still remains very high. And that's just because we've given it hard coded. So there's nothing which could have been improved. Any questions till now? Okay, let's look at the second variant now. Homoscedastic noise, but which is learned from the data. So this specific model case will help you understand the motivation behind writing some of the code that we have written that way. So now sigma also becomes learnable. But the important thing is that sigma is again not dependent on the data, right? Sigma is learned independently. Right? So there is no connection going from this MLPs to the sigma node. It will go in the next case, which is known as the heteroscedastic noise. But still homoscedastic, still a constant number which you will finally use, but you can optimize over it. So now what are the things you want to optimize in this graphical model? The model weights, which is weights and biases, and then the sigma, right? So thus far we have not seen a situation like this where we have model weights and model biases, model parameters, and then a separate value that we want to optimize over, right? So you have two lists, in some sense you have two lists of parameters you want to optimize. Is that a question? Is that an answer? It won't be trained on log joint. What do you mean by that question? So do you mean that we have not specified a prior over sigma? So the loss function would be a common loss function which captures both the weights of the model as well as sigma. We'll look at it in a second, but we'll be using this exact same loss function as before. But importantly, we are obtaining what estimate of sigma? There are only 3 or 4 estimates we have seen. Point estimate. What kind of point estimate? The estimate which is dash the likelihood, maximizing the likelihood, maximum likelihood estimate. For theta, what is the estimate that we are obtaining? Maximum likelihood estimate. So we are obtaining the maximum likelihood estimate for both theta and sigma, right? So therefore it means we have not specified any prior till now. Is that clear, Utkarsh? So what do you think we now need to change from the previous code? Parameters will have to have sigma, which also mean yes, 2 sigma, in this case 2 sigma. 2 sigma is typically used because corresponding to 95% density in the normal distribution. No, it depends on what you want to show. You want to show the 95% confidence interval, you want to show 68 point whatever percent. It depends on you. That is a subjective choice. But respectively, it's a constant. The proportionality constant may vary, whether you do 1 sigma, 2 sigma, 3 sigma, but it's a constant. Okay, so what all do we need to change in order to learn sigma and theta? So previously, what was sigma? I was giving fixed log noise standard deviation, right? Fixed log noise standard deviation, if you go to the definition where I defined this variable, it was defined on a torch.tensor with some specific value and log of it. Okay. What attribute does this variable not have which you want? Requires grad, right? It is not a parameter, it's a fixed value. So if you just add requires grad to it, you can then use it further. So that is exactly what we'll do. For the second case, which is homoscedastic noise but learned from the data, we will create log noise standard deviation. We have carefully renamed the variable now. Instead of fixed log noise standard deviation, it's log noise standard deviation. It's the torch.nn.parameter, which automatically I think gives you the requires grad thing. The model is the same till now. The model does not change, importantly. The model has not changed. The loss function has not changed. The only thing which we needed to change was move the fixed log noise standard deviation to a nn.parameter, which has a requires grad. Something else we need to change. Again, as good practice, we run the model without training? We run the model without training, again it seems to be working okay. At least the shapes are all correct. And now when we want to give the set of params, previously I had the fixed log noise standard deviation. Instead of that, now I have a tensor. I have a parameter which has a requires grad attribute. This is where the tree leaves code which I had written becomes useful. So we go back to the loss function once. We had parameter leaves equal to jtu.treeleaves of params, right? Params we've been seeing as a nested dictionary till now. So we want to get some tree leaves out of that. Let's see what we effectively get by such a code. So if I run jtu.treeleaves of params, right, it gives me a tensor 0. It gives me tensors of certain shapes, right? Do you think these will be corresponding to 4 biases? This is the 4 by 4 matrix, 4 biases, and weights, and a bias, right? Now, typically, if you didn't use tree leaves functionality, you still want all the set of parameters to be optimized over. Those parameters are 1, log of the noise standard deviation you want to optimize over. The next is you want to optimize over the model dot parameters, right? So you get one list, you get another list, you have 2 lists, and you want to optimize over both of them, right? So you could have done a list 1 plus a list 2, which is an append, concat, whatever you wish to talk. That gives you something like this, tensor 0, right? So this operation is the same as jtu.treeleaves of params. And we can verify this also. jtu.treeleaves of params equal to log of noise standard deviation plus list of homoscedastic model learnable noise dot parameters. Both of them are the same. So that is why we, instead of changing the list of parameters that you're passing, explicitly creating a list around this and then passing it, we just call it jtu.treeleaves of parameters. In params, whatever is contains requires grad will be used in the training automatically through this procedure. So if you were to, just one second, if you were to look at jtu.treeleaves params for the previous model, where we did not have log noise standard deviation as a trainable thing, we will see that that element does not exist. So we can go back and verify this. Right? So can you now see that it does not have a requires grad equal to true here, corresponding to the first element, whereas for the others it has a requires grad equal to true. Automatically now the optimizer will figure out if it has requires grad equal to true or not has, and it will optimize those parameters. Yes, Ritik, you had a question. Okay. So then we can learn these model parameters, and you'll see that the loss has gone down to a much lower number. The loss is coming negative. Does that make sense? How can loss be negative? You've been getting loss negative in some of your assignments also. Why? Okay, log. Okay. Expect such a question in the upcoming quiz with more details. So now if we plot the function and the fit, can you now see that it's a much better fit, right? The variance that you're seeing is roughly corresponding to the variance that you have in the data set, and the fit also seems to be very good at this point. So just by incorporating the sigma to be a learnable parameter, we get the advantage of having now sigma corresponding to the rough range of the data points. Previously we didn't have. Sigma is changing. What is being? Right. So we now just apply gradient descent over it, which means so all you need to do is you go back to the loss function. Let you go to the loss function. The loss depends on log noise standard deviation, which is passed in through the params. For the second case, which is the learnable noise, this is a requires grad. This term has a requires grad equal to true, and the other thing it depends on is the model parameters. So model of x inherently captures the model's thing. So then when you compute the loss, you have in a sense created a computational graph which connects sigma and each of the individual theta i's to the loss, and then you can compute the gradient over each of them individually, and that's how you are able to get the gradient with respect to sigma, the gradient with respect to each of the theta I, and then you apply the simple gradient update rule. In this case, it's done through Adam, but the same thing happens. Other questions?
Sir, in this diagram, there are no connections from the MLP that give the output sigma.
Yes, excellent. There is no connection, but I think what you're missing is that what is the loss?
Loss has a term of sigma.
Loss. So if you were to just extend this graphical model first, so what you'll put a normal distribution with mean mu and variance sigma square, right? So let's assume we put additional nodes here. So we put a node here, which is normal distribution, and then you put the log probe over it. The log probe also contains y as an input, right? So and then you finally obtain the loss, right? Now the loss, if you look at loss, it has connection to sigma, and the loss has connection to mu, and mu is connected to each of the individual weights. So that is the computational graph we're looking at. In the third case, with the heteroscedastic loss, heteroscedastic noise, there sigma is also a function of the neural network inputs, because there we want sigma to vary for a different. So there we want sigma as a function of x. Here we want sigma to be a constant which you want to learn, but you want to optimize that.
So, in other words, can we say that we are using mu to get sigma?
You can say that if you were doing it independently. So if you were to do independently, you can first figure out the MLE for theta and then find out the MLE for sigma independently, right? That's what we discussed when we were discussing Bayesian linear regression. You first find out theta MLE, and then from that you find out the sigma MLE. Here both of the optimization is happening together.
We cannot understand because sigma is connected, sigma is affecting the weights and biases.
Yeah.
And so why is it not connected? Why there are not two nodes
In the last, so in this case, so we want sigma to be independent of x. In this case, because we've said is homoscedastic noise. Sigma can be 4, 5, 7, 10, 20, that I don't care about, but it does not depend on the input x. That is why there is no connection between x and sigma. Other questions? Okay. So if you just wait for 2-3 minutes, we'll move on to that model, and then I think it will become clear why and what we were doing. Any question on this specific thing without looking into the connection between x and sigma? Okay. So we said that we ran through this model and it seems to be doing a much better job. Right. The third one is where now sigma, it's heteroscedastic noise model. So sigma is a function of x, mu is a function of x. So therefore what you can learn is that at some points in the input the noise is very high, the learned noise is high. At some point the sigma x can be low. Right. So let me first show a data set where it might make sense. Let's look at this data set. Can you see that there is much more noise towards the extremes, much less noise towards the middle? And I very purposefully created a data set like this. If you look at the noise, EPS, it depends on 0.1 plus 0.4 into x. Right? So the noise in this case, the generative process, is indeed dependent on the input x, right? Therefore, we get a data set like this, which has more noise towards the extremities. If we were to apply a homoscedastic model to it, we may end up learning something like this. It will be a constant noise. In this case, it's a constant noise. The next one is a learned noise, right? I've learned the noise, but it's still the same constant noise across all the inputs. And this is if we use a heteroscedastic model where we can learn noise which is a function of the input. You can see that the noise is much less over here and much higher over here. So that is the objective. This is what we want to be doing now. And how do we model this heteroscedastic noise? We've said that we have now two outputs from a model, mu and sigma. So therefore, the output layer should have two nodes, mu and log sigma, not sigma. So therefore, the only thing we need to change is our final layer gives, instead of n hidden comma 1, it is n hidden comma 2. And the forward, we say that mu hat, so we say z equal to fc3 of x. And mu hat is the first element of it, the first column of it, and log of noise standard deviation is the second element. Right? We've learned two separate outputs. And now we don't have much to do here. It's the same exact model. We don't even have to pass in any params here because we are not learning anything specific. Everything is incorporated in the model itself. This is how an untrained model looks like. Interestingly, the untrained model is also giving you some sigma which is a function of x. Right? You can see that the noise seems to be increasing as you move from left to right, but it's not useful at this point. And post training, so the loss function, if you see, loss heteroscedastic, this is something which is very good about editors like VS Code. It is putting params in a less thick color. Why do you think that's the case? Unused, right? So I am actually not using params here in this function, but we had kept it constant to match the function signature. So params is just the list of parameters from this model, and the train function just works on that. Nothing new in that. The loss decreases, we get a function which looks like this. Questions? Yeah, you may. So the question is, why might you want to ever use homoscedastic noise? So it's a simplifying assumption, lesser number of parameters, lesser prone to overfitting, and may work in practice for many different kinds of models. In the limiting case, heteroscedastic models should be able to give you homoscedastic noise intervals. Many cases we have practically tried and not always works out. So it's not always true. Sometimes simpler models work out to be better. But in the limit, you would expect this to be always better. Other questions? Okay, so now this was a data set. This was showing, I was showing this on, was still the homoscedastic noise data set. So we will not see much improvement. But if the data set itself contains heteroscedastic noise, which is 0.1 plus 0.4 into x, which is the data set I just showed a few minutes back. Now I'm going to be running different models through this, which I showed a few minutes back. First model is homoscedastic model, fixed noise. So I specify the noise to be 0.5. Right, I get an okayish fit. Post training, I get an okayish fit, not very good. Now homoscedastic model, but learnable noise. So it should do slightly better in terms of the intervals. The mean function would expect to be fairly similar. Right, it does somewhat better. The third one is heteroscedastic model. The untrained one is not useful. The trained one gives you much nicer intervals. Okay, so this ends the aleatoric uncertainty part of the lecture. Any questions on that before we move on to the epistemic one? So Gaurav is saying for heteroscedastic, which one do I need to? Previous data set? Scroll up. It's possible. I mean, so firstly, I think I'm also using a different. So for illustrative purposes, I also created slightly different models where the number of hidden was kept to be 4 for the homoscedastic models. Heteroscedastic one has the default number of hidden parameters to be 10. Hidden layer, the number of neurons in hidden layer to be 10. That could also be causing a difference. So I'd specifically shown you, I'd kept the default to be 4 here because otherwise this would have been insanely large to show. But if I look at the heteroscedastic model, the number of hidden is default kept to be 10. You can modify this, you can try out various things. That's the standard optimization. Generally, more the number of parameters, you want to be able to have more data, more iterations to be able to solve it. That's why it's not always recommended to use heteroscedastic. Okay, now we go on to epistemic uncertainty. So the important thing in Laplace approximation is first to obtain the map estimate. Right? Map estimate of what are we trying to now obtain? Model parameters theta. For simplicity, I will for now just look at the homoscedastic models with fixed noise. But the same techniques will be applicable for all of the other models also. But I'm just keeping life simple for now. So if we have to get the map, it means we have to specify a prior, we have to specify the likelihood, we have to specify the joint, and then we have to optimize the joint. And the optimum of the joint is the theta map. So that's what exactly I've done. I start with negative log prior over the model as an input. I just, for each weight and each bias, I put a toss distribution of normal 0, 1, and I calculate the log prom of the param and do a sum. Right? This is just the standard way of putting a 0, 1 normal as the prior over each of the weight. Negative log likelihood is the same function which we've been using thus far. We have a mu hat, we have a noise standard deviation which I'm passing as an input here, log of that, and then I do the negative log sum, negative log likelihood over the log prom. Right. Negative log joint is the sum of negative log likelihood and negative log prior. Now I was showing this using the object oriented way, right, which starts with the model, and inherently you can then do model of x to get y. Right. But we could have also done this in a functional way, which we'll see in a few seconds. I've created a custom loss function which takes in the model x, y, and params. We get the log standard deviation via the params as we've been doing earlier, and it calls the negative log joint on model x, y log standard deviation. So the earlier code is exactly the same as what we've had till now. And we can obtain an estimate which looks like this. The yellow line that you're now seeing is corresponding to theta map. Right? The standard deviation that you're seeing is currently just the aleatoric uncertainty, which is fixed. Right? This is coming in from the fact that I had said that my noise is fixed log noise standard deviation. I just take an exponentiation over that to get aleatoric uncertainty. Thus far, we have not looked into epistemic uncertainty. We have just, instead of looking at MLE, we have looked at map, but still a point estimate. So what else do you think, what next do you think we need to do? In order to obtain the Laplace approximation. Posterior of, you need to obtain P of D given theta. Theta is all the weights and biases of the neural network. Right? Previously, when we've been looking at Laplace approximation, we've been looking at just univariate distributions, coin toss, etc. Very simple problems. But here, theta corresponds to weights and biases across all the different layers. You want to see the probability of, posterior is theta given D. If you want to be looking at that distribution, but that we can't obtain, so therefore we use the Q of theta. So this is what we had in the slides. P of theta given D might be intractable. Right? So, but we know that P of theta given D is 1 over Z of the joint. So P of D comma theta, comma, and not given, which is just likelihood times the prior and the normalizing constant. So we said that we can approximate this using the Taylor series expansion around the map. So we can say we can approximate the posterior P of theta given D as a normal distribution with mode theta map and the Hessian inverse applied over the negative log joint. Now this begs the question that theta map we have already obtained. Right? What next step do you suggest we do? We know the F bit. The F is the negative log joint. That we already know. So then what do we need to do? Compute the Hessian, right? But we'll make a life slightly simpler. So we'll consider that this is picked up from the Laplace Redux paper. It's a very nice paper. It's a library also, which is used for Laplace approximations for neural networks. So what we generally say is that we start with a deterministic neural network. We can obtain its theta map, and then we want to choose some set of weights to be treated probabilistically. Right? You may want to, the default you may want to think is choose all the set of weights and put a prior over each of them. Right? Each of the individual theta I that you're seeing here is now a distribution instead of being a point estimate. The point estimates we have already obtained via theta map. So they're saying that we could choose all the weights as distributions. We could choose a subset of the weights as distribution. You could choose a specific subset of the weights as a distribution, which is the last layer. Right? This last layer methods turn out to be very quick in practice, very useful and easy to understand. So that's why we'll be looking at the last layer approximation, Laplace approximation. So what we're saying is that only over the last layer there is uncertainty over the parameters theta. The remaining all parameters, they are the fixed to be their theta map values. Right? So if we take this example only, this neural network only, so we'll say that except for the last layer, all of the theta i's have fixed weights. For the last layer, each of them is a distribution. Right? So we want to obtain the posterior over these, over the last layer weights. Then there are various things we can do, like we can approximate the Hessian, etc. I'll not go into that. So this brings us to the goal of computing the Hessian of the negative log joint with respect to the last layer weights. So some of the code may look a little intimidating, a little confusing, little like things you have not seen earlier, but I want you to focus on the concepts. The code you can always look up later. Right? The important thing is compute the Hessian of the negative log joint with respect to the last layer weights. So a lot of the things which I now show is only to be, is showing that with respect to the last layer weight, it's not that easy to be obtained. Purely from methodological perspective. If you were to solve this in maths, like if you were to conceptually show it, it's easy. Just the specifics of these libraries make it slightly tricky to get the last layer weights, Hessian with respect to that. So we'll look at a few things first. One is functools.partial. How many of us have used functools.partial? It seems only 1 or 2 people have used. How many of you have used functools? Okay, why might you want to use functools? Oh, so is that functools? That is func animation. Okay, so functools are a set of tools which make functional programming easier. Functional programming, you can think of the paradigm which treats everything as functions and not a mix of objects and functions. And then you have a purity of functions. So so things like lambda, reduce, operators, whenever you use them, you are thinking more in terms of the functional paradigm instead of the object-oriented paradigm, which many people prefer, I think. But there are purists, and you'll see a lot of folks who want to do pure maths, they will use functional programming like Haskell, etc. They'll use it much more. But anyway, let's come back to the specifics. I wanted to convert this binary string of containing zeros and ones into base 2. I can call this function int of a string base equal to 2, but I can use this function with any base equal to 4, base equal to, default is I think 10, right? So default is 10. So what I want to create is instead a function which specifies which fixes the base equal to 2, right? Int function can take any base. I want to create my own function which hard codes base equal to 2. Right? So I'll say base 2 equal to partial. Right? It creates a partial over the function int where I've specified the base equal to 2. Now it creates a new function. This returns a new function. I call this function base 2 over 1001. It will give me 9. Right? So think of it as whenever you have some functions, you want to constrain, you want to specify some arguments of those functions and want to leave some arguments open-ended. That's when you use partials in functools. Any question on this? Okay. The next is about functional calls. So this is also something which PyTorch has very nicely enabled over the recent few releases. So let's say we have a tiny model which is just n.linear of 3, 1, our input is 2, 3, our target is 2, 1. So you can verify these shapes. 2, 3 goes into 3, 1, you get 2, 1. Okay. So tiny model is just the simple linear layer of 3, 1 and bias is equal to true. And this is typically how you obtain y hat, output equal to tiny model of input. Okay. That's how you obtain in the object-oriented pattern. You will obtain it and you will also get grad function equal to something. Why do you get grad function equal to something? Shouldn't output just be some tensor? Why do we get grad function equal to something? So whenever you're passing through these layers, you automatically compute the gradients. Right? And when you call something dot backward, then it fills on this entry. So this is just doing the forward computational graph creation. And then when you call dot backward, it fills in those values of the gradients in PyTorch. And okay, that's what I'm showing. You create a loss function which is MSE loss. You compute the loss which is over the loss function of output and target. You call loss dot backward. At this point, the gradient information would be available. So you can verify that also because I've not run that code yet. So if I were to do tiny model dot weight dot grad, it does not exist at this point. Right? Only when you call dot backward, then these values come into creation. Right? So we could have computed these weights and biases and the gradients with respect to them in the completely object-oriented fashion, which we've been using, which very used to doing it so far. Or we could have used the functional paradigm. So we create a params, which is a dictionary of the named parameters. So named parameters will give you the key and the corresponding tensor values. I can call this torch.function.functional call. So if you look at the definition of it, it is trying to accept a module, which is nn.module, and a parameter and buffer dictionaries, and then certain inputs. So what it does is it puts these parameters into the model and then calls the model over the input. So you'll get the same output as you obtained here. Minus 0.14, minus 0.53, minus 0.14, minus 0.53. So you get the same result. And I can then call in the loss function of output. The useful thing is, so I can also calculate the gradient in this way. Torch.func.grad. This is more like Jack's way of getting the gradients as opposed to the torch way of getting the gradients. So this is happening via functions. Custom loss function is a function. I compute the gradient with respect to a function over certain parameters, over certain arguments, right? So I obtain the weights and biases, which is the same as I'd obtained here. But the whole point of showing all of this is, using this kind of an approach, I can now compute the gradient sessions with respect to a subset of the weights, which is what we wanted to do. Okay. So let's say I wanted to obtain the gradients with respect to only the bias, right? So in the Laplace approximation code, we'll want to obtain the gradients of the Hessian with respect to only the last layer. In this case, in this tiny example, I want it to be only over the bias, right? So I therefore create this custom loss function. This is a new custom loss function, by the way. It has two arguments, partial params and params. So partial params I just mentioned the dictionary over things which I want the gradient over. So I call params.update of partial params. I create output equal to the same thing as before. And now if you see, I get the gradient only over the specific thing I was trying to create it over. Right? You could use all of this as some boilerplate code for finding out the gradients and Hessians with respect to a subset of the weights. That is the important thing you need to remember, that you'll have to, perhaps there are ways to do this in the object-oriented way, but in the functional way, it's much more expressive, much more easier to understand that we want the gradients and Hessians over a subset of the weights. So therefore, we come on to now the last layer Laplace approximation code. Instead of computing the negative log prior over all the weights, I'm computing it over only the last layer weights. Why is that? Because we assume the other parameters to be deterministic, we assume stochasticity only over the last layer. So therefore, we calculate the negative log prior only over those. Right? So the other part of the code is the same. For each parameters in the last layer, we'll see the partial params would be specified to, let me show you the call. Partial parameters equal to fc3.weight. So we create this dictionary containing the last layer weights. We pass it to functional negative log prior. We pass in the dictionary, and that gives us the negative log prior. Negative log likelihood accepts partial params, model xy log noise standard deviation. We compute the mu hat by the functional call over models and params in x, and we compute the negative log likelihood. So nothing new till this point. Functional negative log joint is just the negative log prior plus negative log likelihood. So the entire set of parameters is the model.named parameters. Right? That's the set of all the parameters. And if you look at the names, fc1.weight.bias, 2.weight, 2.bias, 3.weight, 3. So PyTorch puts them in a very specific notation. And partial params is what I want to specifically use, which is just fc3.weight, and I'm not even putting on the bias. I can also show you what tree leaves on partial params will do. So nothing new at this point. Importantly, the full negative log prior, which assumes stochasticity over all the weights, would be a larger number, as expected, because it's assuming uncertainty over each of the parameters. Whereas the negative log prior, which is assuming a stochasticity only over the last layer, will turn out to be a different, smaller number in this case. The negative log likelihood will be the same, right? Because whether you consider stochasticity over a small number of parameters or over all the set of parameters, that will turn out to be the same. Negative log joint would be different because the negative log prior has changed. This brings us to the main piece of code. I know the map parameters from the optimized model. So Laplace model was optimized over here. Yeah, so we had optimized the Laplace model over here. We took this specific model, homoscedastic fixed noise, we optimized it, we obtained the theta map, and based on the theta map, we plotted the posterior predictive. So, sorry, just the predictive, as well as the uncertainty, which is just the aleatoric uncertainty till now. So, all of this we have done. we take in those set of parameters, which are the map parameters. We know the last layer parameters, which is just a dictionary, and I end up creating a partial function now. Right? So remember what we wanted. We want the Hessian of the negative log joint with respect to the last layer params. Right? What you don't want is the function should also be like, you don't want to be having that over all the set of weights. So therefore we end up creating a partial function where the only thing that you have not fixed, so params you fixed to map params, the only thing which is not fixed is the last layer params. So it's a function of that. Everything else is kept constant, and then through this we can obtain the Hessian matrix. Again, don't get too bogged down by the specifics of the code. You mainly need to understand the concept that we want to get the negative log joint and obtain its Hessian with respect to only the subset of the weights. If you do this, things have changed a little bit because now I've assumed a 4 cross 4, a 4 hidden layer one. Previously it was a 10 hidden layer network, 10 neurons in each hidden layer. So therefore now the matrix is much smaller. So this is the Hessian matrix that you obtain. Now you can obtain the inverse of it. Covariance is torch.inverse of Hessian. Plus I'm adding some amount of regularization. Otherwise many times it's poorly conditioned. You'll not be able to obtain the covariance. And now your Laplace posterior is as you expect. It's a multivariate normal with the mean and the covariance. Right. The important thing again, that everything except for the final layer is deterministic. So therefore the only thing we are putting a posterior over is the final layer weights. Right. And then we can just do Monte Carlo simulation in order to obtain some samples. Like obtain some samples and do Monte Carlo simulation. So we obtained 5101 samples from this Q of theta, which is approximately P of theta given D, where theta is only the final layer weights. So if we do this, we'll get 501 weights of 4 and 1. Forward pass is just putting in these set of parameters which you're obtaining through each 501 different samples that you're obtaining. You put those 4 parameters, 4 weights, you put them in, and then you just call the functional model. You'll get the different outputs corresponding to the different inputs. There's a bit of VMAP magic which I'm doing. And finally, you'll get 501 examples, 501 samples you have to obtain. For corresponding to each sample, you have 100 vector predictions. You can obtain the mean and the standard deviation. And eventually, finally, you'll be able to create a plot like this, which captures the epistemic uncertainty and is also showing the aleatoric uncertainty. To understand this better, first let's just look at the epistemic uncertainty only. So we are just showing 10 samples, the first 10 samples which we had obtained, right? The predictions from the first 10 samples. Each of them is now showing the different theta which could have been used, and corresponding to different theta you have a different model, and corresponding to different model you have a different predictive distribution, different prediction, right? So this is showing the samples from the Laplace posterior, Laplace approximation posterior, and you plug them in and you get the different predictive distribution, different predictions. Corresponding to each such line, you have the aleatoric uncertainty, right? What I'm showing here is just the joint thing, right? So the bluish color is showing the ranges of samples, the ranges of the predictions you could have got for this vector, for the x from -1 to 1. So the last few bit was perhaps a bit too much to digest, so we can go over slowly again, over whatever you want. Yes, questions? We're doing the last layer methods to reduce the computational complexity. The Hessian is a huge matrix to compute generally. Here it's a trivial one. So you also need to understand that you generally have the data in the forms of the model parameters look something like this. Right, this is how typically your model parameters may look like. They are inherently in some nested hierarchical structure, right? Now, one way to obtain the Hessian is to just flatten out each of them into one huge vector. That becomes your entire theta parameter, right? Then you compute the negative log joint and the Hessian with respect to that. So let's say if you end up totally having n parameters in it, you'll have an n square matrix as the Hessian matrix. We have made a very simplifying assumption to only consider the randomness over the last layer. Therefore, we just have the Hessian of the size of number of neurons in the last layer, comma number of neurons in the last layer. But the same code could pretty much be used with a slight amount of modification, because we want to be able to carefully look at these nested structures, flatten and flatten them. That's one way to do. The other is with respect to the partials, which I have shown. Both these techniques could be working. So the question is, instead of the last layer, can we pick up any layer which is critical to the model? I don't know how we may be able to figure that out trivially, which layer is important. One other rationale of thinking about the last layer is, you could think of the first of the last, all the layers before the last layer as a featureizer. You start with your inputs, that creates a feature vector to you, and after that you're doing something similar to Bayesian linear regression now. You're just assuming weights, uncertainty over the set of weights in the final layer. So that's one rationale to think over it. And last layer methods, in the paper they've shown work fairly well compared to the others. They're computationally much more efficient. And if we go back to the specific thing I was showing, there are a lot of other tricks which are required to make this work well in practice, including things like, thus far the Hessian that we have considered is the full Hessian. But you could also assume that the Hessian is only along the diagonal. So all the non-diagonal entries are assumed to be 0. What advantage do you think you'll have if you have a diagonal Hessian? Okay, someone else. Inverses? Inverse is fairly easy. You don't have to do any maths, right? So the inverse of a diagonal matrix is trivially computable, whereas inverse of a full rank matrix is much hard. There are of course other variations like low rank, k factor, which make it easier, but that's essentially what Laplace approximation would require. You would have to choose which weights you want to be treated as probabilistic. The last layer one I think seems like a good default. It doesn't require a lot of computation. You could choose some approximations of the Hessians. There are certain ways to do that. And then you want to be able to get the predictive, right? One way to get the predictive is using Monte Carlo, which we have used. There are other methods in classification also. You could use Monte Carlo. There are certain other approximations you could have used, which are things like probit approximation, etc., which I'm not going to be covering in this course. One very interesting thing which is mentioned in this paper is that hyperparameter tuning, they also optimize the prior in this. Thus far, we have not been optimizing the prior. We have said that the prior is 0, 1. But in this case, they also optimize the prior via something known as type 2 estimation methods or MLE2 methods or empirical Bayes. So there are various names to it. We'll see if at some point we're able to cover this particular topic or not. Yeah. Okay, questions on this notebook? So the TensorFlow probability blog, which I showed a long time back, that was also essentially the same as what we have done. We can start off with models with no uncertainty, which means we learn a line, right? We can start with models which give you aleatoric uncertainty, but this is now fixed noise. You could have aleatoric uncertainty where the noise is fixed, noise is learned. I don't think they're showing this. And then you have epistemic uncertainty, which means you have different functions which could have been created. Each function means different values of theta. Neural network is a function which maps from input to output. So each of the line is one particular function you have created. And then you could have taken both the aleatoric and epistemic uncertainty, which means that for each of the red line, you put that green line plus minus 2 sigma, and then you'll get something like this. Okay, any questions? The code will take a bit of time to digest, but a lot of it you could directly be using it. I am hoping to be able to give something similar to this in your assignments, to use this code, not to implement something like this. And also planning to give something similar to this in one of the course projects, which we'll try and release in next 1 or 2 days. Okay, so if there are no questions, let's